So the work I will present to you, in fact, take place in a bigger project, a project related to formal verifications of algorithms and results in constraint programming. So it started in 2012 with the development in COC of formally verified CP solver. And sorry, I will try to say ROC, but I'm used to say COC. So sorry for that. So first of all, what is some preliminaries? So first of all, what is a constraint satisfaction problem? So it is usually a program that you will give to the solver, and it is a triple, okay, made of a set of variables, a set of constraints to be satisfied, and each variable is assigned a domain that is the set of the possible values. Here, I will focus on finite set as domains. So the main techniques for solving a CSP contain the following ingredients. So you have domain pruning, propagation, enumeration of values, and usually you can see a solver as a systematic backtracking search for variables. So the purpose is to find either a solution or a result that says that your problem isn't sat, and a solution is, as usual, an assignment of variables to values in the domain. The assignment must be complete, that is defined for all the variables, such that the value assigned to the variables satisfy the set of constraints. So when you look at existing CP solvers, we can find different way of representing a domain. So the main data structures to represent domains are range sequences, bit vectors, sparse sets. And my contribution, and it explains the title, is to propose a formally verified implementation of such domains. So let me come back. So regarding range sequences, Ledin and myself have formalized in ROC all the invariant of such a representation, and also all the operations making them yet another formally verified representation of finite sets. For bit vectors, it has already been done in Y3 in COC, and for sparse sets, we can find many implementation in different languages on the web, but as far as I know, there were few efforts to formalize them. So what is a sparse set? So it is a folklore data structure. It is a mutable data structure used to represent finite sets. It has been studied in depth by Briggs and Thorsten in 1993, and it also appears as an exercise in a famous book. This data structure exists in many different variants. For example, you can find sparse arrays, which appear in a verification benchmark in 2010. You have the variant I will study formally, which are used as domains in the CP community. And I would say it is also close to Knus dancing links. So as I said previously, numerous implementations on the web in several languages, and we could find, as far as I know, only a formally verified implementation of sparse arrays in Y3 done by Filiatre and Paskevich some years ago. But this formalization only concerns the basic operation. So what I will present here is a formally verified implementation of sparse sets as reversible domains for integer or set variables. So it is developed with Y3, and we can extract OCaml executable code. So for those who do not know, so Y3 is a framework to do deductive verification. So what does it mean? It means that you have a program, you annotate it with its specification, then to prove the correctness of the program with respect to the specification, the framework will will generate verification conditions or proof obligations, and proving this verification conditions will ensure the correctness of the program with respect to the specifications. And proofs of these verification conditions are in many deductive verification framework done by external provers. And in Y3, so these provers are automatic provers, but also, as you can see on the figure, can also be interactive theorem prover, for example, Coq. So what is Y3? So mainly it is a specification in a programming language called YML based on a polymorphic first order logic. What is interesting in YML? It is that you have polymorphism, pattern matching, exception, mutable data structures with controlled aliasing, but you can manage very easily arrays and so on. It is based on a polymorphic first order logic, so where you can find the possibility to write algebraic data types, recursive definitions, inductive predicates. The specification of the programs are given through contracts, that is precondition and post-conditions. So here requires and ensures properties. And you can also add annotations in your program to guide the generation of verification conditions, or also to prove the termination of loops or recursive functions, for example. And last but not least is the possibility to add ghost code. And this ghost code is very useful to ease specification and proof. And of course, this ghost code is not executable code. It means that when you will try to extract OCaml code or C code, so at extraction time, all this ghost code will disappear. But there is, we say that in this kind of environment, the proof is automatic, but there is nothing like a free lunch, you know that. And in fact, it is auto-active verification. It means that you have to work to achieve this automation. And what does it mean? It means that sometimes you have to add lemmas, to have assertions. You add ghost code in order to guide, in fact, the automation. Okay, so what is a sparse set as domain? So I do not present you the original data structure as in Briggs and Thorsten, but the variant used to represent a domain. So first, an integer domain. So generally in a CP solver, you start to say, okay, the domain of my variable is a range, a finite range. So for example, 0 n minus 1, okay? And then to represent the domain that will be pruned all along the computation, you will use two arrays and a bound. So the two arrays are called dense and sparse, and the bound size d. Okay, so the two arrays are of length n. The two are reverse of each other. What does it mean? For example, if you look at the value 1 in sparse, okay, so the index 1 in this index by 1, you find the value 4. And if you go at the index 4 in the dense array, you will find 1. Okay, so sparse give the location of the values from 0 to n minus 1 into dense. Okay, so you have this property, which is an invariant. It is property P2, which says that sparse of V equal I if and only if dense of I is equal to V. And the dense array is in fact split in two subarrays. The left part, so which is the left part, in fact, contains the actual values in the set D. So, and the right part, let me say it's garbage, okay? It contains values that have been removed during the computation of the solution of the CSP. So here, for example, the real value of D is the set containing the values 3, 6, 5, 2, 1, and 7. And it is the first invariant, so the property P1 you have in red here, that say that the subset which is represented with this data structure is the left part of the dense array, that is a subarray from 0 to size D minus 1. So here are the two invariants that will have to be maintained by the operations on this data structure. Why do the CP solvers use this data structure? It is because we can implement some operations which are very often used in such a context very efficiently. It is the case of the membership test, the remove operation, and also the insertion of an element operation. So if I want to answer as a question, is V an element of D? I just have to look at the value at the index V in sparse and just verify if it is less than size D. If I want to remove a value, it is just a matter of two swapping and a decrement operation. So let me explain you on the example. So imagine I want to remove the value 1 here. So 1 is in the location 4 in dense, okay? So at this location, I found as it is expected 1. So I will swap this value with the last element in D, okay? So, and then I will decrease size D from 1 unit, okay? So you have the swap. And again, I update the second array to maintain the invariant. To add a value, it is something very similar. And furthermore, it is very easy to trail when backtracking, okay? So the only value we have to save and restore is the value of the bound size D. So imagine we are in the situation A, okay? And okay, we do some operation and we would like to come back to this situation. So we will store the value of size D, which is 6 here. Then we do some operation, okay? We do some pruning, so we remove 1, 6, and 3. And the arrays have changed, okay? And size D is now equals to 3. And then I would like to come back to the first situation because I have to backtrack. So the only things to do is to put size D to 6, okay? And so the value interesting of the dense array is this left part. So now it is, okay, different from D0 in the initial situation, but it is a set. So the order does not matter. You have a permutation. In Y3, what does it give? Mainly, we will have to define a type for sparse set, and it is this type, okay? So you will find as in any programming language, you will have a record with n, so the big N of the previous slides, the two arrays, dense and sparse, array of integer, and the bound size D, okay? And you also have an additional field in this record, which is set D, and it is a ghost field. So it is here just to specify our properties. And in fact, it is the abstract model, okay? And set D is here defined as a mathematical set of type F set int. So it is a mathematical finite set. And this type has an invariant part where we will put some invariant properties. Okay, so I have tried to keep the colors so you can find the P1 value and the P2 value, and the black one are some, I would say, typing more or less typing properties. Okay. Is it enough? No. Okay. So from there, I will have to verify that the type is inhabited. Okay, it's very easy. Put everything as empty. And as soon as I will have an operation that manipulates sparse sets, I will have to preserve all the properties in the invariant, okay? So now, okay, I would like to implement the delete function, okay, that remove an element, but I would like also to implement an undo operation, okay? And to implement an undo operation, this is not sufficient. How do I say that I would like to come back to a previous situation? I can only say that if I have kept all the states before, okay? So I will add a new mutable ghost records called states, and states is a partial function that associate to each cardinality of the abstract model, the abstract model. It is not for each, okay? It is for the situation, for the cardinalities I have already met. So I will have a bunch of constraints on this partial function states, okay, which are described here. So the domain of definition of this partial function is included in this range. So cardinality of the current abstract model to n. The current state must be stored in it. Each stored state is well-formed and contains ZD, and there is a link with paths, okay? That says that if I have recorded that S has been encountered with cardinality I, then it means that for all X, we can say that if its location in the left part of dense is less than I, then it is equivalent to X belongs to S. It was not so easy to find this property. And in fact, I could only find it when doing the proof. Okay, so I will illustrate that on the two operations, remove and undo. So here is the remove function. So, okay, the two swap I have shown to you some slides ago, and the decrementation of the bound size D. Now I add the contract. So the contract, you can see, it is an abstract contract. It deals with the abstract model, that is the set, the mathematical set. And in order to prove that the invariant on the type of sparse set is maintained, I will have to add ghost code in order to maintain this additional ghost fields. Okay, so here we just remove from the abstract model the value v, and we update the partial function states, saying that yes, we had as an invariant property that the current situation must be recorded in the partial function. So it is what does this last instruction. Okay, so the verification conditions will effectively to check that the invariant is preserved by the operation. The precondition of set to arrays are satisfied because I call this operation, and when I call an operation, as it is a modular verification, I have to prove that the precondition of these functions hold. And after executing the operation, of course, we have to prove that the postcondition is satisfied. So the same for undo. So the code is extremely simple. Okay, just do an assignment of p to the variable, to the bound size d. Okay, I had the contract. Okay, so the first line is a precondition, and I will specify that yes, I would like to come back to the situation where the cardinality of the set is P, but this situation must have been encountered. And if it has been encountered, it means that P is in the domain of the function, the partial function. And then at the end, I would like to have a sparse set which correspond exactly to the situation where the cardinality was P, okay? And same as before, I have to update the ghost field of A, and just have to, for example, to say that, okay, now the abstract model is the value that was registered in the partial function. Okay, if I do like that, I will be in trouble at extraction time, because when you extract code, all the preconditions and so on are erased, okay? And so it means that I may broke, the invariant may be broken, okay? So this is not very satisfies. It is not. We do not want that. Okay, so I will remove this requires in order to have a defensive version. So in the code now, I will check that P is a size already encountered. But what does it mean? It means that we have to deal with the previous size of the bounds. So it means that size D must become a reversible integer. What is a reversible integer? It is a record, again, containing the actual value and the list of previous values back, okay? And you have a bunch of invariant properties on this value and back. And it is really implemented like that in CP solvers. And so after some modifications, we arrived to this final type for sparse array. So you have everything we had before with size D replaced by size D dot value. And furthermore, we have this new blue invariant property making a link between the domain of the partial function states and the value we can find in this reversible integer. And again, we have to replace this simple assignment by a call to a function that updates the reversible integer. And the function may return, may raise an exception when the value P is not valid. Okay, so I specify, implemented, and proved 19 operations. So it's a simple one, but also the set operations, the classical set operations. All that is freely available, and it's not so big, I would say. So just 830 lines of code with a ratio around 4 lines of logical annotations for 1 line of computation. All this has been proved with the solvers attached to Y3, and here I used CVC4, Itergo, and Z3 using the strategy auto level 2. And I think if you do the sum up, it was 524, I think so, verification conditions that were generated, and the time is not so huge. Okay, is it enough to have executable code? No. Okay, yes, I could have it, but I would like to have efficient OCaml code using the int type for integers, so machine integers and not mathematical integers, because previously it was mathematical integers. And I would like also to have an array, the array of OCaml. So again, I have to message the specification of the programs. And it's not difficult, it's just a burden, okay, because you have to do the same thing, replacing int by int 63, replacing array by array 63. But okay, at the end of the days, everything is proved, everything is okay. And here, in fact, I was lucky because I had no overflow verification conditions that were generated, because in fact on the integer we just take them and we move them from one location to another one and so on. We never do computation on them, so no overflow. And they are all less than n, which if I can give it to OCaml, it means that it is a right integer, so no problem. This code has been used on a small for implementing a naive simple Sudoku solver, originally written in OCaml by Jean-Christophe Filiatre. And this example is quite significant because it makes an intensive use of backtracking, so the undo operation here. Okay, if you remember, at the beginning I said I can also contribute to have a formally verification for set variables. So this kind of variables mean that they have a domain which is a finite set of integers, okay? And you have a dedicated set constraints in different solvers. And the same kind of things apply, okay? So here, the abstract domain is not a finite set of integer, but it is a set interval, okay? In fact, so it is described by two sets, rec and pos, where rec is a set of required values and pos is a set of possible values. And the sparse set I've presented to you previously can be adapted to represent the domain of set variables. So it is more or less the same, but instead of having one bound, you have two bounds. Okay, so here size 1 delimiter the set required, and size 2 delimiters the set of possible values. So if you look at this example, what does it mean? It means that the set interval, which is represented here, so is described by the two bounds, which are the two sets, in fact. So the values 0, 2, 3 are in each possibility of the set, and the value 0, 2, 3, 1, 4, 8 are the possible values, okay? The invariants are more or less the same. So P2 is exactly the same. So the two arrays must be reverse of each other. And the red one, so P prime 1 is more or less P1, but for the two subarrays. And furthermore, you have to have this relation because the possible value contains the required one, so the bounds must be in this order, and that's it. And what does it give in YML? It is exactly the same. It's a bit more complex because instead of having one reversible integer, you have one pair which is reversible of two integers. You have two abstract sets as a model, but the property which are invariant are completely, I would say, copied, okay? As the operations, I have proven this one, how to create such a domain, how do you exclude one value, how do you require one value, and so on. And these operations are inspired from an existing solver, which is called Oscar. And everything is proved in Y3 and extracted to OCaml. So here is the summary. So I have developed a formally verified implementation of sparse sets as domain and sparse subsets using Y3. So it's a sparse subset. I forgot to give the name, but it is the name given when we want to represent set variables. I have also formally verified the implementation of sparse sets as defined by Briggs and Dorset, using Y3 again. So it is the original data structure and property. What is the difference? In fact, the property P2 is relaxed. You have it, but only on the left part of the array. So the code is available online. And for future work, as I said before, in Y3, you can also extract C code. I would like to try this kind of extraction. This extraction mechanisms to C is less developed than the one to OCaml in Y3. So maybe some problems, but we can try to do this. The community, the CP community also use a mix of bit vectors and sparse sets, which is called sparse bit sets. And I would like to look at this variant too. We already have some things in Y3 about bit vectors. So maybe I think it's not so huge work. And I would like also to integrate this family of data structure with in the framework developed by Alain et al. About snapshotable stores. So that this is a framework that allows an arbitrary set of references to be captured and restored all at once. So it can be very useful to mix this with sparse sets if you want to implement backtracking search for solvers. Thank you.
Thank you very much. So when you changed to the machine integers to make the extraction work, you said you had to make some changes to the specification. Is there still some more abstract specification that didn't change? I mean, or how can you make sure that it's still this specifying the same properties?
So, the specification has not changed.
Okay.
The only thing that have changed is this for all x of type int. Now it becomes for all x of type int 63, right. Meaning that I restrict the specification to the machine integers.
Okay, right. But that was the only change. Okay, yes. Then I thought you had to change other things as well.
Yes, and as I was using array of integer, it is the same for the array of machine code integer. But okay, the fact that we are always between the bounds and so on, all this is already verified with the previous version.
I mean, it was nice that you didn't have to change the proof.
Yeah, yes. Some proofs were more difficult to obtain, but I just had to wait longer.
Okay.
Longer.
It was all automated.
Yes, yes, yes.
The add operation, is that also undoable?
No.
And does that then also change the reversible int so that you can?
In fact, you are right, because in a CP solver, you don't have values, but I manage the operation add also. But when I do an insertion, I say in some sense, I say stop, you cannot backtrack anymore. And so I will empty the state's partial functions. In a way, it looks like, okay, I reset the system and I can start again. But backtracking is lost at that time.
Thanks.
More questions? Thank Catharina again. We have finished